everyone. I'm going to go ahead and introduce our speaker. We have Dr. Chiang Zheng. He's an assistant professor in the CSE department at our school, University of South Carolina. He received his PhD in computer science and engineering from Penn State University. His main research interest is computer system security with a focus on Internet of Things and mobile computing. He is also interested in adversarial machine learning. He usually publishes his work in a wide range of conferences and journals, including CCS, NDSS, Mobicom, MobiCS, and PLD, etc. Thank you for accepting to give a talk in the seminar series. The floor is yours. Thank you.
Thank you for the introduction. And thank you for coming, everyone. Today I will be presenting our work recently presented in Usenet Security 2021. And the topic is about anomaly detection in smart homes. And this is quite a long title, so please let me interpret it a little bit. So first, the semantics. What does it mean? I assume our main audience is the students in this class, so I do not assume too much security background. All right, so I will explain little by little. Right. So what is semantics? Semantics, just a meaning, right? The meaning. It's relative to syntax, right? When I say 72, in terms of syntax, it's an integer, right? But if I tell you, it's temperature, suddenly it makes sense. It makes a lot of sense, right? Not only an integer, but it means some temperature. That's a semantics, right? So if when you receive an integer, okay, you know it's just an integer. But if you annotate it, this is temperature, then it gives you a lot of useful information that you could use, right? That's an example. Anomaly detection. Of course, we will go over what kind of anomalies we will be talking about. No matter it's due to the device failures or attacks. Okay, so we consider very strong threat model. Not only the device failures, but also intentionally attacks. Finally, amplify. What does it mean? That means that in this smart home, you install quite a few automation apps. What is the automation apps? What's the automation rule? That kind of the same thing. But does anybody know examples of this? Like smart home app, smart home automation rule.
Control and free.
Yeah. If you don't mind, could I take off my mask? If you don't mind, if you don't like it, just let me know, right? So this will make me much more comfortable. Anyway, so I will keep some distance. Anyway, so let me give you an example. Like, if the motion is on, turn on the light, right? That is one of the simplest apps you can install. And then when the motion is off, after 20 minutes or after 15 minutes, you turn the light off. Why? Why don't you want turn the light off immediately? And you give a delay? Because very probably you will come back again. And you don't want to turn it off and on back and forth, so that you can you would not hurt, damage the light, right? Anyway, those are the examples of smart home automations. And when you install such kind of automation apps, automation rules in your smart home, we call it amplified smart home, which is very, very popular nowadays with the millions of users. Next, let me go over some background about IoT. Right? So let's look at this graph from bottom and it goes up. So at bottom, because it has no difference from the traditional device, like temperature sensor, a light bulb, a relay, which turn off and then turn on something. But since it becomes interesting when you look up one more layer, that you with those physical devices, you also interconnect them with some chips, which can issue some commands to turn it on and off, which can read your sensor values and represent it into 72, an integer, right? Then those chips, they will follow some specific protocols like IP, ZigBee, Z-Wave, right? Then finally, which is very popular, also which makes this a big thing, that nowadays there are hundreds of IoT platforms. What does it mean? Like Apple, they provide a platform. Samsung, they provide this kind of smart things platform. What do? They allow you install the automation apps I just mentioned. You do not install your apps on those kind of cheap devices, which is $10, $20. No, you cannot do that. They are so cheap. You cannot do this kind of smart things. You install those automation apps on Apple's or Samsung's or like Amazon, Google's, those kind of cloud platforms. Then we will have two major information flow. One is from the device to the, for example, Apple's cloud, or like Google, Amazon's cloud. So those kind of information goes up. That's the event. So the device reports the current status, like, oh, the temperature is 72, the light is on, okay, the door is open, so on and so forth, right? Then it becomes very interesting, because you have smart apps which subscribe some kind of devices. For example, you have an app that subscribes to the motion sensor, and this app does this thing. If motion is on, and the illuminance sensor level is low or under some certain value which is configurable, then you turn on the light. Then it generates command. Then we have the other information flow from the IoT platform goes down to the device. That's the other information flow which issues this command to finally turn on the light. Next, test time. What will happen next? So since you turn on the light will report an event, right? Then you go back to that the other information flow, right? From the device to the IoT platform. So it follows this two information flow to do this kind of smart automation, which makes your home convenient and secure. What does it mean by being secure? Because a lot of home security systems like SimpliSafe, they also rely on this kind of architecture. For example, when nobody is home, but a door open is detected, then you will trigger a siren and report this event to the police station if you pay the monthly fee, or at least it will generate a siren, right? Alarm. So you can always see there are lots of potentials. Even the irrigation systems nowadays become smart. When I detect, oh, the soil is dry, and in future 2 or 3 days there will be no rain, then I automatically turn on the irrigation system. Or when I find, oh, it's 10 p.m. but the garage door is still open, I will automatically close the garage door. And finally, for example, if I detect there's water on the floor, then I will shut off the valve, shut off the water flow. So on and so forth. You can see there are lots of potentials. What I said is limited to smart homes. You can easily extend this to smart lab, smart office, smart factories, smart farms. Think about this. So it's estimated that this is going to be $1 trillion market. Okay, $1 trillion. Another Android research hot topic, right? Another cloud computing research topic. After that, we have even another one, right? What I mean is that in previous years, people spend a lot of efforts, right, in studying Android security, and cloud computing security. Now we can safely predict that this is going to be another hot one, okay, as hot as Android and the cloud computing, right? So Anyway, that's background. Any questions so far? You can interrupt me anytime. All right. So, of course, the field is about the IoT, but the problem is anomaly detection. What kind of anomalies? Let me give you some examples. See here, what if the valve, the water valve, shut off? This command is intercepted by attacker. Then we consider this is an anomaly because the valve does not follow the command. Why? Because the command has been intercepted by the attacker. As a result, the room will be flooded. That is an example for anomaly. You can see the consequence, right? And secondly, you want to turn off the heater. For example, the temperature is high enough. Then you are supposed to turn off the smart heater, but it's not. Why? Because physically, it's a physical broken relay does not work. It even has no business with this kind of smart things. It's kind of physical thing. It doesn't work. And then the temperature will goes high and higher and higher. It may have the potential, not necessarily, but it may have the potential that it will cause the fire, right? And thirdly, a lot of users, they use their presence sensor, okay, either like their smartphone, right, with some app or some specialized device to show the location of the user. So if the user is at home or near the home, then you automatically unlock the door. But what if that presence sensor has been hijacked by the attacker? Then the attacker can go into your home, right? So that is even another example of the IoT anomalies. Those are just examples. But if we look at the categorization, it becomes more interesting, right? We consider two main categories. That is, one is due to the IoT device malfunctions. The other is due to attacks. And if we look at the IoT device malfunctions, we have 40 events. What does it mean? It means that the light is not on, but it's reported it's on, right? And the ghost command, what does it mean? It means that mysteriously, during the midnight, your lights in your bedroom is turned on. Nobody can explain. Nobody wants that, but it's turned on. And it's reported a lot of times on this kind of smart home platforms, communities. Event losses, right? Of course, it means, for example, we give an example, right? Your some events has been intercepted. Command failures, right? We also talk about the physical part failure. We give an example that the broken relay. Also, your chips may also have failures because it's so cheap. $5, $10 kind of IoT devices. You cannot expect too high. No, it's not like a $100 device. $10, $5 IoT devices. They are kind of unreliable. So they may have this kind of cyber parts, physical part failures. If you look at the device alarm, okay, no matter if it fails or not big deal. But what if that device, the events, is to trigger some more security sensitive device? Then it's gonna be serious consequences, right? What if, for example, the presence sensor is very cheap, but it's used to control your lock, right? Although your lock is over $200, it's kind of you can expect a high about that. But unfortunately, you use a very cheap press sensor to control your lock. Okay, $10 device to control $200 device. Okay, which makes attacks much easier. Right? It do not need to target the lock. The lock is maybe so secure, it's hard to compromise. But how about the presence sensor? $5, $10. And this also shows why the IoT security becomes so important, because if the attacker compromises your computer, yes, they can steal information. That is unfortunate. However, could it launch any physical attack? Could it make a fire in your house? No. Could it make a flooding in your house? No. Even your laptop you compromise? No, it cannot that. But suddenly, because the IoT devices are closely coupled with your physical environment, so your IoT failure will be extended into a physical failure, fire, flood, so on and so forth. So that's why IoT security is so important. And in addition to IoT device malfunctions, we also have attacks on IoT devices. For example, like what if the events and the commands are fake, right? As I said, the light is not on, but because the light has been compromised, it's a report on. And the light may be not so sensitive. How about the lock, right? How about the heater, right? And what if your event and the command have been hijacked, have been intercepted and discarded by the attacker, right? What if I have compromised your device, I totally control your device, and you send me a command, and I refuse to execute the command, but I lie that, oh, I already followed that command. You asked me to lock the door. I said, oh yes, I did that. I even report, oh, lock it is down, but actually it's not locked. Think about this. And denial of execution, yeah, stealthy execution. That means that, for example, I compromise this sensitive device, for example, to unlock the door, but I don't report anything. You even don't know whether the door has been unlocked or not, because I'm silent. I keep stealthy. So look at this. If you only try to come up with a solution to focus only one of the malfunctions or attacks, that's doable. That's not so challenging. But the challenge is that we simultaneously target all the attacks, all the malfunctions. That makes our research challenging. Okay, also of big significance, right? So follow me and see how we resolve it. Before that, let's first take a look at the related work. Okay, any question, by the way? No? Okay, go ahead.
So why do they use cheap IoT devices to, like you were mentioning like the chips and stuff, they're like $5. If they're unreliable, why do they use them? Is it just because they're cheap or?
Because it's convenient.
Okay.
Right? Yeah. And then because of the cheap.
I figured that was it.
If it's expensive, very few people can afford it, then it will not become so popular, right?
Yeah.
So this is the market, right? Anyway, so let's take a look at the related work. So alarm detection is not new. Even IoT alarm detection is not new. So people have done a lot of work. So what did they do? They use this kind of data mining or machine learning techniques. So basically, they take the event logs as the input, then they train a system. Okay, usually a machine learning system or data mining model. Then next time, when some other events come, they can predict whether it's corresponds to alarming or not. So it works in some occasions, but it also has a lot of limitations. First, the smart home system is complex, with, for example, with hundreds or even sometimes thousands of devices, if you consider a smart farm, smart factory. Which means that you're gonna need a huge amount of data to make the model finally stable, right? Second, it's gonna be very difficult for this kind of machine learning data mining to learn very complex smart app. Let me give you an example. If the motion is off, then after 20 minutes, you turn off the lights. Think about how can the data mining model, machine learning model precisely learn 20 minutes? Right? You're gonna need a lot of data. 19, what happened? 21st, what happened? Right? So on and so forth. This is just a simple example. You can consider a lot of other configurations. It's going to be very difficult for your data mining or machine learning to learn a whole bunch of such configurations. But what if you use app analysis? You analyze the app that has been installed by the user. Immediately, you will see the semantics. You can immediately make use of it. for the anomaly detection. Of course, how, right? We will talk about that later. And another big advantage is that overall it's a black box model, which makes it unexplainable. You don't know why it's a report an anomaly or not. You don't know why it's a false positive, why it's a false negative. Because the input is a whole bunch of data, the output is just a result. In the middle, like millions of parameters for the deep learning. How can you interpret it, right? And it's very difficult to update because users may move around the devices, they may install, delete, update this kind of smart apps. Then you're gonna need another whole bunch of data to make the model stable. But in the meanwhile, consider that actually by app analysis, you can immediately know how the user has updated the apps, right? Like a huge amount of data versus like an instant analysis. Right? That's a big difference. So that is the traditional approach. So what's our approach? Our approach is that we found devices are correlated over a lot of channels, different channels. We summarize at least 3 channels, like a smart app channel, like based on the app, the device should coordinate like this way, right? That's the smart app channel. Then we have the physical channel, which is even easier to understand. Like when the heater is on, temperature should be up, right? Question?
Yeah, I have a question. Why at all we need resistance if you can add feedback loop? For example, if user says lock the door, we can have, for example, light sensor, and if there is light, it means door is not locked. If there is like this shaft and no light goes between sensor and LED, then the door is locked. So why we can't just add this feedback loop and say, okay, if command sent but door is not locked, so light still can go through, it means this is anomaly. But if user says close the door and we send the command lock the door and light don't go through, it means there is a shaft, so hence the door is closed.
Right, that's exactly what I'm going to present. The thing is, yeah, when you do something, you will affect other sensors. Then based on the other sensors, you can infer back what has happened, so on and so forth. But the challenge, I will talk about that, how to represent it in a, for example, for human, it's going to be very easy to understand what you just said. But how can a machine do this kind of things? That's what we will talk about, all right? Yeah, be patient, all right? So for the physical channel, yeah, it's easy, right? Like when the light is on, the illuminance should be high, right? Now when you push the door, right? Then the accelerometer sensor, accelerometer, right? Each phone also has an accelerometer. They can sense it, they can report, oh, it's active, so on and so forth. And the user activity channel, it's very interesting, right? But think about, if the TV is on, probably there's somebody sitting on the sofa. Or maybe it depends on the home, but at least you can train your system to see whether it's true or not, right? And for example, when somebody is cooking, at least you can predict, oh, the user is present, the user is home, right? Otherwise, it's going to be a tiger who is cooking, right? So anyway, so this kind of channels can be understood as the correlations, relations between this kind of device states and the events. That's what we will be making use of. But the thing is how, right? We have a series of research questions. So first, what semantic information can be used? And how to capture and represent the semantic information. The second one is the most challenging one, which gives us a lot of troubles. We spend like over a year on this single question. Thirdly, once you figure out the second one, the third one is easy. How to make use of it for anomaly detection. Right? The second one is the most challenging. I said we spent over a year on this because we tried a different method, but all failed until this one. Anyway, so based on what we just talked about, the channels, of course, you can analyze and capture the semantic information from each channel. For example, based on the apps installed by the users, you analyze the app. For example, in this example, we have the water detected. Then you should issue this command, that is you shut off the valve, right? That is you analyze the app. Of course, this is a simple example. Secondly, you can see if this is connected with a smart plug, right? If the smart plug is connected with a smart heater, let's assume like this. This is not necessarily true. We will talk about this challenge because this is not necessarily true. Sometimes a smart heater is connected to a smart plug. Sometimes the smart plug is connected with the TV. Who knows? You don't know, and you cannot ask the user to write this down for you. It's not usable. It's not doable, right? So anyway, it could happen. So if this is true, then we can infer a lot of information. For example, if the heater reports it's off, but the power reports high, then it contradicts, right? It does not make sense, right? And also, if for example, power reports low, but the heater reports it's still on, right? It's working, then also it does not make sense, right? So, and finally, the user activities is kind of simple because we turn the user activities into some devices, for example, presence sensor, motion sensor, which all can reflect these activities. So the second channel, third channel, we handle them in a uniform way. So now let's look at the app analysis. Okay, that is a separate topic. I will not talk about this here. Of course, we did that, but I will not talk about that in detail. And plus, it's not our contribution because we used some existing technique. The second and third channel, how to extract and capture semantic information, that is our contribution, and that's very interesting. See, for human, it's gonna be very easy to understand. Okay, a temperature and a heater, they should have a certain relation. The light, the illuminance sensor, they should have a relation, right? The door, when you push the door, and the accelerometer, they should have some relation. For human, that's easy. But the thing is that if you rely on the human, you're gonna have a lot of cost, right? Human manual effort, tedious effort. Secondly, you hardly guarantee it's complete. And the code has a lot of errors, so on and so forth. So we propose this kind of automatic approach. We use NLP technique, specifically use word to vector. How? The good thing, fortunately, for each capability for acceleration, you describe some capability in those smart home platform. There's some description. Okay, when the acceleration happens, what will happen, and what happens will trigger the acceleration. They have this kind of description. And for example, SmartThings has this kind of description. Amazon also has this kind of description because why they need this? They need to document this in order to let all the developers who want to connect their platform to understand what each capability means precisely. Okay, they need to help the developers to understand what it means. So we make use of the existing documentation, we analyze the text, and we use the NLP techniques to find whether two capabilities have a very close relation. That is, they are very close in terms of their embedding. Right? Everybody knows embedding, if you work on AI, is close in the higher dimensional system, high dimensional space. If so, we know, we give a check. Otherwise, we do not give a check. Then we will propose hypothetical correlation based on that. For example, given a heater and the temperature sensor, we will hypothesize that they are correlated. Of course, it's not necessarily true, but fortunately, don't forget that we still have event logs, right? We will make use of the event logs to further examine whether this hypothesis should be accepted or not, right? That is the two steps. First, we come up with this kind of hypothetical correlations. We don't need the user provide, oh, whether this temperature sensor and heater, they are close together. No, we don't need that. We will rely on the event logs to automatically tell us whether this hypothesis should be accepted or not. That is our innovation. Very interesting, actually. Secondly, even you have that, how to represent it, right? Because smart apps has its semantics true, but its semantics you can conveniently represent in this way, but the device relations you can represent in another way. But does it exist a uniform way? Right? That's the question. How to represent in a uniform way so that your system can use it in a very convenient fashion, right? So yes, we found that. The challenge is semantic information is diverse, right? We have this smart app semantics, physical channel semantics, user activity semantics. We represent all of them into this kind of a correlation between one event and another event or state. And for some very complex semantics, we support you can add and some condition here to support very complex logic. We can do that, but the overall scheme is like this. When you have this event, it should be followed by, this means followed by another event. If you have this delusion, it means that you have this event, then this device must be in this state. Let me explain this. For example, if water is detected based on the app installed by the user, you should expect a valve closed event. Right? That makes sense, right? This is what the app tells you, right? And if the power is high, then it implies that the smart heater is on. Of course, see, we assume this correlation has been examined, this hypothesis has passed the event logs checking. So it has been accepted, so you can see that. You can have a high confidence that, oh, if the smart plug reports power high, then you can infer that the heater is on. And if the user is present, then if this event is received, you can expect very soon you can receive another event. Why? Because when user arrives home, it will open the door and push the door. That context sensor is installed on the door, on the front door, to tell whether there is somebody pushing the door. All right. So those are the correlations we use. This is the representation we use. Next, we will discuss how those hypothetical correlations are verified using event logs. Very simple, actually. We use this hypothesis testing. If given this hypothesis, we consider it's a null hypothesis. If this null hypothesis means that, okay, illuminance is high, but the light is off. Okay? If it happens more than, for example, 5% of what this is configurable, if it happens more than 5%, we know, okay, this hypothesis is false. This hypothesis should not be accepted. It means that the two devices probably do not have relation. Right? For example, this illuminance sensor is in this room, but the light is in another room. So then we should reject this hypothesis. Otherwise, we should accept the hypothesis. Right? This is how we derive these correlations. But how about the correlations due to smart apps? Oh no, for that one we don't need event logs because it's certainly true. If it's not true, it only means there's something wrong. All right, because you should follow the code. Right? The code writes like this way. All right. And finally, when should we end?
We have time. And then 3.5 would be fine. So
oh, 3.5. Okay. Now, how to make use of it? It's we will conduct this kind of contextual and consequential checking. Two kinds of checking. What does it mean by What does it mean by contextual checking? It means that when an event you received, I will check whether the context, this kind of this means implies, this kind of implied correlations are all satisfied or not. For example, when the power high is received, I will check whether the heater is really on. If it's yes, of course there are no anomaly. Otherwise, if it's a mismatch, we know there's some anomaly. For example, I want to turn off the heater, but because of the broken relay, the heater is not physically turned off, then I should report an anomaly. Why I know it's an anomaly? Because the power is still high. It violates this kind of in the cyberspace you tell it's turned off, but physically it's not. Then I find, oh, this correlation has been violated. That is a contextual checking. Also, we have a consequential checking. That is, if there is water detected, we should receive a valve closed event very soon. If it's violated, we know there is an anomaly. Right? That is how we make use of the correlations. Since we don't have that much time, okay, this is an example of just a subset of hundreds of correlations we capture from a smart home. We totally, in our evaluation, very comprehensive. We involved 4 real-world smart homes, not like testbed, real homes, okay, with the real humans inside it. We have 3 weeks of training and 1 week of testing. And this is just one of the real smart homes, real-world smart homes. And for example, in the first smart home, we captured hundreds of correlations. This is just a subset. And what we are proud of is our precision and recall, which is very high. Why it's considered high? It's significantly higher than the baseline, the prior work. 97 versus 2%, 17% precision. We are also very surprised why the work had such a low precision, still got published. We don't understand, but that's true. And okay, this is for each anomaly case. What's the precision, the recall, the breakdown of each case? Right. So our contributions are threefold. We propose to use semantics from multiple channels for anomaly detection, including the app channel, physical channel, and the user activity channel. And we resolved actually the second one is the main challenge. We represent this kind of diverse semantic information in a uniform way. We call it correlations. We use a code analysis, NLP, and finally hypothesis testing. Finally, this is the first accurate non-black box IoT anomaly detection systems, and it got a very high precision and recall, and explainable because it's correlation by correlation. Human can examine it, all of them. Each of them makes sense. Look at this. Each of them makes sense. If it does not make sense, you can tell it. It's not like millions of deep learning parameters. No, it's correlation by correlation. All right. Any questions?
I'm gonna check Teams and see if you have any questions there. I think we're good. So do you guys have any questions here?
The question is, do you have standardized system for sensors and readings and formats? They should be like published and read, or you have it just for any system given some rules what sensors you have and how they connected to each other. So is there any standard rules or protocols for messages and communication between physical devices?
Oh yeah, there are some standards, ZigBee, Z-Wave, or Wi-Fi. Yeah, those are the 3 main ones. Also you have Bluetooth, but that is not the mainstream ones. ZigBee, Z-Wave is the most popular one, but nowadays the IP or Wi-Fi based devices become more popular.
So are you target them all by your approach, or you pick specific ones?
Our approach is agnostic about this kind of protocols, because after all we just make use of the event logs. And now we got event logs. we don't care whether what kind of protocol they use.
I see. Thank you.
Right.
Any other questions? So I have a question.
Uh-huh.
So I assume that the anomaly detection is happening in the cloud, right?
In the what?
In the cloud, or we have a distributed system. So
It's in the home. It could be in the home. It could be during the network transmission phase.
but the entire the algorithm that you run to detect that anomalies, where is that happening?
Oh, that's on the cloud. We assume like the Apple or Samsung, this IoT cloud platform is trustworthy, it's secure, it's not compromised.
Okay.
But the network, the IoT device itself, the home cannot be trusted. Yeah.
And do you plan to do, if that's the case, because the transfer of information is important too, do you plan to do any adversarial, to handle adversarial attacks for these cases too? Because the data that is going to be processed can be, attacked too, right?
Yes, we already done a couple of works assuming the IoT. What if the IoT platform they abuse the data they collected? For example, we have all our data that are flowing to Apple, to Samsung, to Google, Amazon. Yes, some of you may say, that's fine, but think about it. They have all your privacy. They even know at what time you go to the restroom. So some people are not comfortable with that. So we already published some paper, for example, in NDSS that resolve this privacy concern.
Okay, so but that could be, when I'm thinking about it, that could be interesting if we have some processing unit in each of these IoT devices and implement this NLP, for example, like this model that is going to do the process as a distributed machine learning. This way you don't have to send the data out to any cloud.
Right.
That can be processed locally as well.
Yeah. That's also another architecture called a local platform. We have an open hub. And actually, Apple mainly perform this kind of local execution, although they will also send your data to the cloud. So that's why when you pull your phone, you can see the status of your home. So yeah, in terms of the program execution, there are already some platforms doing that, local execution.
Interesting. Any other questions? Thank you very much again.